For our next topic here in our crash course, we have your bonding in organic compounds. Remember, here we are going to discuss hybridization, bond properties, electronegativity, and bond polarity. So this is quite a relatively shorter discussion. So particularly, see hybridization and bond properties, they are somehow related. So later, we will emphasize the different hybridization scheme that our organic compounds adapt. So let's start our discussion here in our bonding in organic compounds. So class, as an introduction, let's just watch first the short video on our hybridization discussion.
The shape of the new sp3 hybrid orbital is best characterized as 1 part s and 3 parts p. As with all orbitals, think of these hybrid orbitals as three-dimensional shapes, where you can find the electron 90% of the time. The hybridized carbon now possesses 4 unpaired valence electrons and is said to be an sp3 hybridized carbon.
Class, again, in hybridization, the 1, 3s and the 3, 3p orbitals, the valence electrons of your carbon atom, will blend together to form 4 new equal energy orbitals that we call your sp3 orbitals. Okay, the energy of these new orbitals is in between your original 3s and 3p that we will see later on.
When we superimpose all 4 sp3 hybrid orbitals onto the carbon atom, it becomes quite cumbersome and confusing. Thus, we simply show how the electrons in the hybrid orbitals are oriented in 3 dimensions. The 4 new hybrid orbitals attempt to get as far apart from each other as possible, 109.5 degrees. Think of this as the orbitals attempting to minimize repulsions between them. Thus, they are oriented towards the corners of a tetrahedron with all angles at 109.5 degrees. Your instructor will often draw the sp3 hybridized carbon on the blackboard as shown.
Class, again, I would like to point out, for your sp3 orbitals, its geometry, as you can see, is tetrahedral, and the angle between your sp3 orbitals are approximately 109.5 degrees, okay?
The 2 solid lines in this drawing are in the plane of the board. The wedge represents the electron coming out of the plane of the board, and the dashed line represents the electron going back behind the plane of the board. Each of the 4 sp3 hybrid orbitals contains 1 electron capable of forming a covalent bond. The sp3 hybridized carbon is now capable of forming 4 covalent bonds.
Alright, so that's it for our introductory video for our hybridization. Class, our reference hybridization reaction is usually the formation of your sp3 hybridized orbitals. And with that, ayan, to supplement our video, of course, when we say hybridization again, this is a very important concept that is used to explain and determine the bonding and geometry of our organic compounds. So class, our reaction here involves the mixing of your different orbitals. Particularly, this is usually our s and p orbitals in order to form a new hybrid orbitals that have equivalent energy. Class, don't forget, our hybridization is stabilized by your covalent bond. So remember, if we hybridize your 1s orbital and your 3p orbitals upon hybridization, our 4 hybrid orbitals will have similar energy. And if you will observe, class, the energy is in between the energy of your original 1s orbital and 3p orbitals. Okay? So class, in terms of our shape of your s and p orbitals, this is relatively the formed hybrid orbitals. Recall, from inorganic or Gen Chem, we know that s orbitals, they are spherical in shape, and for our p orbitals, usually class, they are dumbbell shape. And this hybridization directly influences the molecular shape, your bond angles, the reactivity of our organic compounds. That's why it's very important that as early as now, you are familiar with how we hybridize your s and p orbitals. So far, we just focused on your sp3 hybridization. So let's take methane as an example for our explanation and discussion here. So as you can see for methane, sir, it only has single bonds. Yes, that's correct. Particularly, we have 4 CH bonds that are covalently bonded with a single bond. So before we form this 4 covalent bonds, of course, this is the original structure and shape of our hydrogen and carbon atoms. Class, the 4 lobes here correspond to your 4 sp3 hybridized orbitals that have equal energy. Okay? So again, this is a tetrahedral geometric molecule. So upon reacting with your 4 hydrogen atoms, ayan, this is the structure. And remember, in terms of our bonding, the carbon will carry an sp3 hybridized orbitals, particularly 4 sp3 hybridized orbitals colored here in yellow. For H class or hydrogen, remember, it only has 1 electron in its structure, and it is particularly your 1s. So for your CH single bond, we have your carbon at sp3 hybridized, and your hydrogen carries 1s orbital. And that is actually our formation ng sigma bond. Class, when we say sigma bond or recall from Gen Chem, that's your head-to-head overlap of your 2 orbitals. And for your methane, particularly, we have a tetrahedron or tetrahedral geometry. Okay, so remember that, class. Additionally, aside from your CH bonds, let's take your ethane molecule as an example. See, we have a new unique bond here, your CC single bond. For ethane, of course, this is very obvious. So for our sigma bonds, for ethane, this is our original mechanism. So coming from our individual atoms, 3 hydrogen atoms and 1 carbon atom for our particular group here, and another set of 3 hydrogen atoms and 1 carbon atom. That corresponds to this structural formula. Again, class, upon reaction, let's see. Your CH bond and your CC bond, of course, will form your sigma bond. Again, this is your sigma bond head-to-head overlap. And usually, class, in your overlapping, we form a cylindrical symmetry. Particularly here, it's very obvious. Again, for ethane that has 2 carbons, we have an additional sigma bond. Your C2C single bond, its specific hybridization, particularly of your carbon atom, is sp3 hybridized orbital. That's very specific for your CC single bond. Clear? Class, again, here, your carbon still carries the tetrahedral molecular geometry. So therefore, the bond angles are still 109.5 degrees apart from each other. Let's try visualizing the formation of your hybridized orbitals for our sp3 orbital. Check. When we hybridize your 1s orbitals and 3p orbitals, this is the specific interactions in your hybridization that occurs. As you can see, your p orbitals dumbbell ang shape, your s orbitals, it is straightforwardly a spherical orbital. Okay, so aside from this visualization, let's also take or discuss the formation of our sigma bond. See class, ayan, that's the cylindrical symmetry in your formation of your sigma bond. For instance, in your CH bonds and in your single carbon-to-carbon covalent bond. Clear? So class, that's it for our sp3 hybridization. So let's now move forward with your sp2 hybridization. So recall, for sp2 hybridization, from its name, we will just mix 1s orbital and 2p orbitals, okay? So sir, what will happen with our one remaining p orbital? Class, that will be left unhybridized, okay? And remember, that unhybridized p orbital will be the one to form your pi bonds, okay? Let's just take our discussion slowly. Let's take our alkene ethylene functional group as an example. So class, evidently we still have your CH bonds here, your typical hydrocarbon single bonds, that is your sigma bond, okay? So again, this is the origin of our sigma bonds in our ethylene structure. So for ethylene, this is our functional or our visualization, sorry. Again, for the sigma bonds, we have your carbon. Check. Its hybridization now is sp2, while your hydrogen will still retain its 1s orbital. Class, again, this is sp2 because one of the p orbital is left unhybridized in order to form the pi bond between our double bonds here. Okay, so again, for your double bond, we also have a sigma bond. And that particular sigma bond is your carbon that has sp2 orbitals. Class, for your sp2 hybridized carbon, as you can see in its structure, it is trigonal planar in terms of its molecular geometry. So usually, it carries the bond angle equal to 120 degrees. So meaning, our sp2 orbitals are 120 degrees apart from each other. Okay? So class, again, for your sp2, we also have the formation of pi bonds. Class, this is colored in violet. Again, this is the side-to-side overlap of your unhybridized p orbital. So if we are going to compare the strength of your sigma and pi bonds, class, much more stronger ang sigma bonds. Remember, that's a head-to-head overlap or head-on overlap. So relatively stronger. For your pi bonding, it's just a side-to-side overlap between the lobes of your p orbitals. So for your pi bonds, ayan class, the orbital is 2p bonded with another 2p orbital. Recall, that's the unhybridized p orbital of your carbon atom. So class, to summarize, this is our available or formed sigma and pi bonds for our ethylene or in general for the organic compounds that have double bond in its structure. So for our total visualization, check, ayan. So class, remember, we have your sigma bond here, the sp2 sigma bond, and for the side-to-side overlap, the 2p orbitals will form our pi bond. Class, remember, ang double bond ang source of our pi bonds here. Alright? Okay, so that's it for sp2 hybridization. So let's also visualize what happened upon hybridization of your sp2 carbons. Let's see. For sp2, from the name itself, the only orbitals that will participate are your 1s orbital and your 2p orbitals. Class, again, that's just a straightforward reaction. So usually naman, similar lang ang shape ng different hybridization schemes natin. Their main difference is the number of p orbitals that participate in forming your new hybrid orbitals. Next, the formation of pi bond usually occurs again through your side-to-side overlap of your two lobes in our p orbitals. That's why, comparing it with your sigma bond, class, remember, it is relatively weaker. Check, again, we will form the overlap side-to-side for our unhybridized p orbitals. Okay, so class, again, this occurs when your atoms are in sp2 hybridized orbital. Alright, so remember, for a double bond, we have one bond that is a sigma bond, and we have one bond that is a pi bond. So for our last hybridization scheme, we have your sp hybridization. Check. Again, we already discussed this particular feature coming from your sp3 and sp2 hybridized orbitals. Sir, question, what is the unique hybridization here in your sp hybridized orbitals? Let's take your acetylene compound as an example. Remember, in terms of your functional group, acetylene has a triple bond. Alright? Class, again, your sigma bonds arising from your CH and CC bonds will still be applicable here in our acetylene compounds. But remember, the hybridization of your carbon now will carry the sp hybridized. So sir, meaning 2p orbitals will be left unhybridized. Yes. That's why for your triple bonds class, we have 2 pi bonds. Okay? And that will originate from our triple bonds in your structure. Let's see what are the unique features here in your sp hybridized carbon. Check. We again have your CH orbitals or your CH sigma bond, sorry. And again, for your triple bond, we have your CC, CSP or SP orbitals and one of your C2P orbitals. Ayan. So class, for your C2P orbitals, that's your 1 pi bond. Sir, what is the origin of the other pi bond? Class, that's still your triple bond. Check. Ayan, that's our two side-to-side overlaps of your two unhybridized p orbitals. As you can see here, we have an additional 2p orbitals for your triple bond. Class, let's summarize again our sigma and pi bonds here for our triple bonded organic compound, acetylene. As you can see, here we have your CH bonds. We also have your CC bonds, and those are your sigma bonds. For our carbon triple bond, we have two sources of pi bonds. First one is your overlapping here, colored in violet. So that's just simply your 2p interaction ng sp hybridized, the 2p orbital carbon. Other sources is the other C2C, 2p orbital. Class, again, for the triple bond, we have 2 pi bonds and 1 sigma bond for your CC, CSP sigma bonds. Class, for your sp hybridized orbital, as you can see, linear ang molecular geometry, so that's why our bond angle for our substituents here is around 180 degrees apart from each other. For our visualization, check, we only have one s orbital and one p orbitals here in order to form our sp hybridized carbon. Class, let's summarize the hybridization geometry here in our next slide. Again, as I emphasized, for your sp3 orbitals, we have a tetrahedral molecular geometry with a bond angle approximately equal to 109.5 degrees. So they are 109.5 degrees apart from each other. So that's your sp3 orbitals. Next, we have your sp2 hybridized orbitals. So we discussed this, trigonal planar with your molecular geometry and the hybridization, of course, we have your bond angle equal to 120 degrees. And lastly, for linear, again, that's very specific for your sp hybridized orbital. Class, again, for linear molecular geom, coming from your discussion in Gen Chem or in organic chemistry, your bond angle is approximately 180 degrees. So for your sp orbitals, ang regions ng electron density, as you can see here, 2. For your trigonal planar, check the hybridization, we have 3 lobes. That is equivalent to 3 electron-rich regions. For your sp3 orbitals or hybridized orbitals, we have 4. That is corresponding to your 4 sp3 orbitals. Class, let's summarize the very important information here on our hybridization discussion. Let's check. Ayan, in terms of your hybridization, the orbitals involved from the name itself, sp3, 1s, 3p. For sp2, 1s, 2p. And finally, for sp, we need 1s and 1p in order to proceed with our hybridization. Class, very easy lang yan ha. Please remember it. For geometry and bond angle, check, we discussed this on our previous slides. So please remember this because annually, this appear in your board exam. And in the boards, that's just really a straightforward question. So you will be asked only with your molecular geom ng specific types of our hybridization. But now, let's proceed with our number of sigma bonds. When we see number of sigma bonds, class, this is particular with the capability of your carbon atom to bond through formation of sigma bonds. For sp3 again, we have 4 sp3 orbitals. That's why we have 4 sigma bonds here. For sp2 orbitals, class, again, sp2 we have 3 sp2 orbitals because the other one is a unhybridized p orbitals. That's why it is only capable of forming 3 sigma bonds and 1 pi bond. Again, this is for your 1 unhybridized p orbitals. Class, I hope it's clear. For sp3, check again, wala tayong wala tayong pi bonds. Lastly, for sp, we have 2 sigma bonds coming from our sp hybridized orbitals. And for your 2p orbitals that were left unhybridized, that will be the source of your pi bonds. Clear? Again, our typical examples, we have alkanes like your methane and alcohol like methanol for your sp3 hybridized orbitals. So as a rough generalization, class, usually ang sp3 orbitals, they are just composed of single bonds. Secondly, for sp2, usually they have double bonds in their structure. For instance, we have alkenes and carbonyls. Remember, for carbonyls, that's just a carbon doubly bonded to oxygen. Check. Here we have your alkene, particularly your ethene. And here we also have your carbonyl containing compound. Our simplest aldehyde, of course, that is your formaldehyde molecule. Lastly, for sp, usually they carry the triple bond like your alkynes and nitrile. Alright? So class, we discussed already our summary of your hybridization. Remember, for sp3, usually single bond. sp2, they usually have double bonds. And lastly, for your sp hybridized orbital, triple bonds in their structure. For our next slide, this is already in your manual, di ba? Class, remember, as our generalization, your sp3 hybridized orbitals, they are usually in your single bonds. Let's check briefly our table here in our presentation. For alkane, sp3 orbitals, single bond. For alcohol and ether, ayan class, very obvious ang single bonds. That's why we have sp3 hybridization. Next, we have amine. Remember the structure of amine, single bonded with your nitrogen atom. That's why it's also sp3. Class, please take some time to read the notes. So I will not going to discuss this further because this is just a supplementary discussion. Your notes and example are already provided in your manual. Let's proceed with our sp2 hybridization. For your alkene, for your carbon atom in particular, sp2 because of the presence of double bond. Diba? Class, next example, for our carbonyl. For your carbon and oxygen atom, both of them carries the sp2 hybridized orbital. Okay? So again, carbonyl containing compounds, we have your aldehydes and ketones. Thirdly, we have your carboxylic acid that carries your sp2 hybridized orbital, particularly in the carbon. Because class, your carboxylic acid also is a type of your carbonyl containing compound. Diba? Remember? And lastly, for amide, class, similar, that it also contains a carbonyl compound in its structure, particularly also with your nitrogen atom. So both of your carbon and nitrogen can carry sp2 hybridized orbital. Class, I would like to point this one out because your amide has a resonance capability, both of your carbon and nitrogen can carry the sp2 hybridized orbital. Okay, so again, that's your partial sp2 hybridization. Clear? Lastly, for your sp hybridized orbitals, we have alkyne, and we also have here nitrile. Class, we only have 2 relevant examples for your sp hybridized orbitals, and both of them have triple bonds in their structure. Okay, again class, please take some time to revisit our discussion on our notable example of hybridization in our particular functional groups. Clear? Ayan class, for our next topic, in order to transition, let's discuss our did you know segments here. For our did you know, remember that not all bonds are created equal. O, di ba my favoritism? Some are tighter, some can give you space. O, sir, what does that mean? Again, class, that depends on your hybridization process. O, let's read this briefly, ha? Hybridization affects more than just the shape of our orbital, as it changes also the bond strength and length of our covalent bonds. Okay? In particular, this is the important thing to note here. Your sp hybridized bonds, they are shorter in terms of their bond length, but they are stronger in terms of their bond strength. Ooh, so sir, sorry, they are inversely proportional. Yes, if your bond is shorter, well, obviously it is a strong bond. Consequently, for sp3 hybridized bonds, it has a longer bond length and therefore, class, of course, relatively weaker ang bond strength niya. Class, remember, for your CC pi bond, it is relatively weaker, okay? And of course, your hybridization isn't just about structure. It's also about your strength and stability of your covalent bonding in our organic compounds structure. For this topic, this is our transition with the bond properties. All right, class, remember, for bond properties, we have your sp3 hybridized, sp2 hybridized, and lastly, sp hybridized. Remember, from your previous slides, our rough generalization, check, ayan. For your sp3, usually, longest ang bond length, but weakest in terms of their bond strength. For your sp hybridized, you have a shortest bond length, while strongest bond strength. O sir, how about sp2? Class, moderate lang yan. Moderate bond length and moderate bond strength. So in terms of our trends, your bond length will increase from your sp to your sp3 orbitals. And on the other hand, for the bond strength, it will increase from your sp3 to sp orbitals. Class, as a summary, they have inverse relationship, okay? For our percent S character, this is based on our hybridization scheme. Let's check. For sp3, total number of orbitals, how many? We have 1s and 3p orbitals for a total of 4 orbitals. And in order to determine the percent S class, how many among the 4 orbitals is an s orbital? So yung obvious naman, 1 lang po. Very good. That's why for your sp3 orbital, its percent S character is around 1/4 or 25%. Secondly, for sp2 orbitals, a class, similar analogy. How many total number of orbitals? 1s orbital, 2p orbitals for a total of 3 orbitals. And with these 3 orbitals, how many is s? Of course, obviously, only 1. So that's why around 1/3 ang percent S character ng sp2 orbitals, or that's just around 33%. Lastly, for sp orbitals, we have 2 total orbitals, 1s, 1p. And of course, class, we have 1s. For our percent S character, we have 50% S character. So to generalize, for our bond length, as you increase, okay? As you increase your percent S, your bond length will become shorter. For bond strength, as you increase your percent S character, your bond strength will also increase. Class, again, that's our analogy here. Remember, as you increase percent S character, increase ang bond strength, particularly for sp hybridized orbitals. Ayan. Please remember this one, class, as we are going to proceed with our discussion on our summary ng bond properties. Class, don't never mind our percent P character. So again, ang total characteristic ng ating hybridized orbital is 100%. So in order to determine the percent P character, just subtract 25 from our total percentage of 100. Diba? 100 minus 25, that's just 75. And the similar strategy can be applied for sp2 and sp orbitals. Let's check. For sp2, remember, 33%, around 1/3 ang percent S character. And for sp, class, 50%, relatively higher ang percent S character natin here. Ayan. Thirdly, again, for bond strength, lowest or weakest si sp3, strongest or highest si sp. For bond length, longest si sp3, shortest si sp. I hope, class, you can get a good grasp of our discussion in bond properties. Very important po in order to build your knowledge for our next topics, your stereochem and our numerous organic reactions. Class, again, typical bonds for sp3 single, sp2 double, and sp triple bonds. So to wrap up our discussion here, we have a sample problem for our bonding in organic compounds. Let's read. Xanthalbic acid, a fatty acid isolated from the seeds of the sandalwood tree, is an unusual fatty acid that contains a C to C triple bond. Class, again, that's your xanthalbic acid. It's unusual because it contains triple bonds. The question is, rank the labeled bonds in order of your increasing bond strength. So we have 3 labeled bonds here, A, B, and C. Class, check the hybridization of each carbon that participates in the formation of your bonding. Okay, so again here, remember, we are concerned with your carbons that participate in our single, double, and triple bonding. Ayan, so sorry class, medyo struggle ako mag-draw. Ayan. For now, I will flash the answer. Remember, increasing bond strength. So the weakest here is our A bonding. Sir, what's the reason? Because the carbon here, class, again, it's hybridization, it's just sp3. The carbon here is, class, we have a single bond, so that's an sp2 carbon. So the bond here is your sp3, sp2 carbon, relatively weaker compared to your B and C bonds. Let's check. For the next label bonds, we have your bonding C. Sir, what's the reason? What is the hybridization between our bonding C? Here, sp3 single bonds, but here, this is your class guess. That's an sp hybridized orbital because of the presence of triple bond. Comparing it with your sp3 and sp2, relatively stronger ang sp3 sp hybridized orbitals to form your covalent bonds here. So obviously the strongest bond is the one in our label B. So what's the reason? Let's check the hybridization. For this carbon, sp2. For this carbon, sp. Again, sp2 because of the double bond and sp because of the triple bond. Class, again, as you increase the number of bonds, your bond strength obviously will also increase. So class, here also in our discussion of bonding, it's important to somehow touch on your topic on electronegativity and polarity from your inorganic chemistry. So remember, brief recall on our formal definition of electronegativity. So simply that's just the measure of the attraction of your atom, particularly for the electrons that participate in a bond. Recall, we have nonpolar and polar bonds. Here, In our organic chemistry discussions, we are particular with the determination of the polarity of your CC single bond, CH single bond, and the CO bonds. Class, remember ha, when two identical atoms are bonded together, they attract electrons equally resulting in a non-polar bond. So sir, really, almost similar ang electronegativity ni carbon at ni hydrogen. Yes. Class, again, CH bonds are considered non-polar because your difference in electronegativity, 2.5 and 2.2, class, relatively minimal yan. Okay? On the other hand, when atoms with different electronegativities bond, your electrons are shared equally. Check, diba? Comparing your oxygen and carbon, well, oxygen is more electronegative. In particular, in a CO bond, electrons are drawn toward oxygen with an electronegativity value of 3.4 compared to your carbon na 2.5 lang. So class, electron-rich si oxygen and here, electron-deficient si carbon. That's why it will carry a partially positive charge. Diba? We call this your dipole or charge separation. So I hope you still remember your discussion in organic chemistry. So for other visualization technique, see, for non-polar covalent bond, almost shared equally ang electrons natin here with our electron density shapes of, or electron density map, sorry, of your HH bond. Particularly for your polar covalent bond, ayan. So your electrons, as you can see, they are attracted to your more electronegative chlorine atom. Class, again, this is just a brief recall of your electronegativity. Next. For inductive effect, this is very important in our discussion here in inorganic chemistry because your acid strength is actually influenced by electronegativity through your inductive, first one, and resonance effects. Okay, class, the difference here, inductive effect is done through the sigma bonds participating in your bonding interactions here. Let's check ha. Ayan. Firstly, we have your ionized compound here. So no electronegative atoms to stabilize the conjugate base because class relatively, they have similar electronegativity for your hydrocarbon chain. So for your oxygen, its electronegativity is somehow nearby with our, or near with our carbon and hydrogen electronegativity. Now, on the other hand, if you have CF3, ayan, CF3 substituent, here it is, it will withdraw electron density through sigma bonds, thereby stabilizing the conjugate base here in our molecular structure. Remember class, your F will withdraw electron density. Okay, so again, the withdrawal or donation of your electron density is through your sigma bonds here due to your electronegativity differences. Okay, ang mechanism. Electron withdrawing groups, such as your halogens, will pull electron density through your single bonds or your sigma bonds toward themselves. So, diba, for instance, now we have this molecule, and of course, this is a stronger acid compared to your molecule here. So, what is this molecule? So, that is your conjugate base ng ethanol. Diba? So, again, more stable ang conjugate base ni CF3, CH2OH molecule. So that's your trifluoroethanol class. Remember, that's through your inductive effect. Diba? Our visualization here, ayan, your carbon, they play, okay? They play tug of war against halogen. And remember, they will eventually lose with your halogen because your halogen is a highly electron withdrawing group. Class, again, that's your inductive effect. Our mechanism is through your sigma bonding. Okay, again, electron withdrawing groups pull electron density through your sigma bonding. And the effect, as from our previous slides, it will stabilize the conjugate base by reducing the electron density. So if you have a stable conjugate base, of course, the acid is stronger because mas favored ang formation ng conjugate base. Sorry. Ayan. Class, next. Resonance effect, diba? For resonance effect, this is already in your inorganic. So again, for resonance, we are talking about the delocalization of electron density now through the pi bonds naman. Diba, recall, for inductive, sigma bonds. For your resonance, we have your pi bonds or lone pairs. See, lone pairs across adjacent. So required na adjacent? Yes. Here, your resonance effect can be illustrated in comparing the acid strength of your ethanol and your acetic acid. Plus, resonance stabilization makes your acetate, okay? The acetate is the conjugate base ng acetic acid more stable than the conjugate base ng ethanol, our previous example. So obviously, much more stronger acid, see, acetic acid. Again, negative charge will be delocalized over your pi bonds or multiple atoms through resonance structure. And of course, similar with the effect on acid strength, stabilization on the conjugate base here by our specific process of delocalization. So what's the result? Again, it will increase the acid strength of your compound. Class, remember ha, this is our typical example of, acetate ion resonance. As you can see, your electrons can be delocalized here in our lone pairs between our adjacent oxygen. Clear? To test your knowledge, let's answer this sample problem. So let's see, arrange the following compounds in order of increasing acid strength. First one here, we have your acetic acid, okay? Here we have your dichloroacetic acid, and as you can see, we also have here your monochloro or your simply chloroacetic acid. Class, in terms of their acid strength, increasing down. So here, the less, okay, or the weaker compound, of course, is the acetic acid only. Remember, it has no electronegative group such as chlorine that can pull electrons. So that's the weakest. Class, what's next? So remember, the difference here for our next two compounds is the presence of the chlorine atoms. One compound carries two chlorine, and one carries one chlorine. So of course, class, chlorine is an electron withdrawing group, so it will favor the stabilization of your conjugate base. That's why ang next acid natin, of course, stronger lang po si chloroacetic acid. As you can see here, your 1 chlorine will stabilize the conjugate base via inductive effect. And lastly, for dichloroacetic acid, class, very strong acid yan because of the 2 chlorine that will withdraw electrons. And as a result, it will really stabilize or it will enhance stabilization of our conjugate base. Alright, so this is the strongest acid between our 3 molecules. Clear? Next sample, again, increasing acid strength, we have your formic acid, we have your ethanol, and we have your acetic acid. Sir, I think the weakest acid is your ethanol because wala siyang resonance stabilization, di ba? That's correct. In terms of resonance stabilization, ethanol lacks that stabilizing interaction. Oh, what's next? Between acetic acid and formic acid, which is a relatively stronger. Again, class, after ethanol, we have acetic acid. Hala, class, actually, that's a major point of confusion. But again, your CH3 class, that's an electron donating. So the carboxylic acid with a methyl group, of course, is somehow a stronger acid lang. Okay? Because of the presence of your alkyl substituent that is actually an electron donating, thereby destabilizing our conjugate base. And finally, obviously, class, this is a stronger acid because it lacks the electron donating alkyl group. O see, it only has 2 hydrogens in its structure. Please remember, class, formic acid is stronger comparatively with your or comparably with your acetic acid due to lack of electron donating alkyl group. Okay, and lastly, we have your last set of compounds. We have your ethanol acetic acid and your mono chloroacetic acid or simply chloroacetic acid. Class, always weakest ang alcohol ethanol because it has no resonance and it has no electronegative or highly electronegative or electron withdrawing group. What's next between acetic acid and your chloroacetic acid? Class, it's already here. Diba? So again, between these two, as you can see, we have this substituent acetic acid first before your chloroacetic acid. Clear? Again, class, your inductive effect and resonance effect can affect your acid strength. All right, and that's it for our discussion in bonding in organic compounds. So let's summarize what we have discussed here so far. Again, firstly with hybridization, check. For sp3 class, let's test your knowledge. The geometry, tetrahedral, and the bond angle 109.5 degrees apart from each other. Class, in terms of your bond types, how many sigma bonds and how many pi bonds for sp3? Again, since we have 4 sp3 orbitals, we have 4 sigma bonds and 0 pi bonds. Class, I would like to point out the pi bonds, this will originate from your unhybridized p orbitals. For sp3, we do not have that unhybridized p orbitals. Okay? Class, lastly, percent S character, how much? Again, 25%, and this is common for your single bonded functional groups such as alkanes, alcohols, and amines. Okay, next, sp2, what is the geometry and bond angle? Ayan, trigonal planar and 120 degrees. For the bond types, how many sigma bonds and how many pi bonds? Recall, sp2, we have 3 sp2 orbitals and 1 unhybridized p orbital. So, sir, their answer here is 3 sigma bonds and 1 pi bond. That's correct. Remember, pi bonds will originate from your unhybridized p orbital. Okay, class. For the percent S character, remember, 33%, and usually this is a double bonded functional group such as your alkenes and carbonyl. Okay, lastly, sp, the geometry class, remember, linear with 180 bond angle. For the bond types, for sp, we have 2 sp hybridized orbitals and 2 p unhybridized orbitals. That's why, ayan, class, please familiarize yourselves with the bond types and the number of your pi bonds. Again, for sp, 2 sigma bonds coming from your 2 sp orbitals and 2 pi bonds coming from your 2 p unhybridized orbitals. Class, recall, in terms of the percent S, how much? 50%. And remember, triple bonds usually see sp hybridized orbitals. That's your alkynes and nitriles in particular. Class, for our discussion on electronegativity and polarity, class, let's test your knowledge through this definition question here in our Lars words. Okay, first one, the tendency of an atom to attract electrons in a bond, we call this your, starts with letter E. Ayan, that's your electronegativity. Next, atoms have equal or similar electronegativity. Class, that's your nonpolar bond. And of course, if we have nonpolar, we have your polar bond wherein electrons are shared unequally due to your electronegativity difference, such as in your CO single bond. Again, that's your polar bond, class. Next, this results from unequal sharing of electrons, creating partial charges. So somehow, class, this is under your inorganic chemistry. Starts with letter D. We also call this your separation of charge. We call this your dipole moment because of the unequal sharing of electrons. Clear? For the next item, this is the electron withdrawing atoms that stabilize negative charge. Class, keyword here, sigma bonds. Sir, I remember that's particular for inductive effect. Very good, class. Again, that's your stabilization of conjugate base through the electron withdrawing nature via our sigma bonds. Class, again, electron withdrawing, usually they are halogens. All right, let's continue. The localization of electrons stabilizes conjugate bases. So if we have inductive effect, the other effect or other factor that can affect acid strength is resonance effect. And lastly, this is increased by electronegative groups, inductive and resonance effect through stabilization. Class, I already said the answer. That's your acid strength. All right, so finally, we are done with our crash course number 1. Class, very lengthy, easy crash course 1 because this is more on knowledge building crash course. All right, so with that, ayan, so time out muna, sir, with your PT1. Again, class, this will cover your intro, your nomenclature, your bonding in organic compounds. So for PT1, we have 10 items for 15 minutes. Again, class, please practice closed manual answering. And also time yourselves in answering your practice test. So class, again, we are done with Crash Course 1. So I will see you on our next video. For now, please take some time to review and to take some rest for our next discussion. So class, I will end the video first. Please answer your practice test 1. Bye, class!